All right, welcome back, nerds. Today, no, all right, a couple of people liked it. So we have these positive ions and negative ions. A negative ion has a particular name. A negative ion, what do we call it? Anion, A negative. The cation is the positive one. Okay, cool. So as we go through here, there's a bunch of little pieces that we're going to look at. It turns out that as we look at these ions, they like to bond with nonmetals. So let me look ahead just a skosh so I can see if we want to really address the where does that electron go now, or if we want to save it for later. We're going to address it now. We'll hit it again later if we have to. Okay, so here's what I want us to think about. Let's pick something from group 1 that's easy to draw and not hydrogen. So let's do a quick example and actually address that question. And this was Lily's. Where does the electron that's gained or lost, where does it go? Okay. Now, just to be really clear, I'm talking about these electrons when we're working out these charges, because the electrons are moving, right? Okay. So let's consider lithium, which as we're looking at this, lithium is Li. And we'll draw this here in a second. I want to try to combine this really quickly. Lithium is group 1. Pick something in group 17. Fluorine. Okay. This is like the beginning of chemistry, and it ties a little bit to physics. Yes, sir? Yep, sign out on the back. Okay. All right. Fluorine is F. Now, for this, I am only going to draw the dot diagrams, the Lewis dot diagrams from our previous chapter, which only electrons that I care about are which ones? The valence. So the fact that lithium exists in group 1 says how many valence electrons does it have? 1. Are there 8 dots around my lithium right now? So is it stable right now? No. And we've already decided it can either gain 7 more electrons, or it can do what? Take away 1. Okay. So I'm going to switch colors here very specifically only with the electrons. Fluorine is an F. How many valence electrons does fluorine have? 7. Okay, so 1, 2, 3, 4, 5, 6, 7. Everybody cool with that? Okay, I want us to think about what happens here. Remember, stability is like key to everything. The universe wants to be stable. These are in the universe, and they want to be stable. Just like you want to be stable, I assume. Okay, neither of these are stable yet. What do we say lithium has to do to get stable? If it gets rid of 1. And the question yesterday was, well, where does it go? What does fluorine need to do to become stable?
It needs 1 there.
Well, where do you think this electron goes then? So let's move this real quick. If we see that lithium, and I'm going to personify, which means I'm going to give this human characteristics. There's no real thought to this, though, from their point of view, to my knowledge. Okay, lithium is going to give, lithium gives electron, and specifically it's 1 electron, to fluorine. Okay, yes ma'am.
So if lithium gives 1 electron to fluorine, does that mean it also becomes stable?
Yes, 100%. Love it. Lithium, when it gives this 1 electron over here, it's now stable. And this is the weird one, because if you took an electron from lithium, you now only have 2. But look at element number 2 and tell me which group it's in and whether or not it's stable. Helium, in which group?
18.
It's stable. So at 2 with that one only. So check it out. We now have lithium, and I'm not going to draw any valence electrons anymore, but it's stable. Now there's even more to this. If it was neutrally charged, 3 protons, 3 electrons, that's a charge of 0, right? And it's given away an electron, so it's minus the negative. What's its charge now? It had a charge of 0, and it gave away a negative.
Oh, no. Oh,
Try
wait,
again.
no, plus 1. Or just 1.
3 protons and 2 electrons now.
Oh.
Positive 1, right? I'm going to put a plus right up here to indicate that it's now positive ion. This is a cation at this point. Okay, where did that electron go?
Fluorine.
to fluorine. So I have the ability to just copy and paste, so I'm going to seize that. Here it is, and now I'm going to draw my extra electron that physically moved. And I can see it moved. Now, Ashley's question was awesome. She said, will lithium be stable now? 100% yes it will be. What about fluorine?
Yeah.
How many electrons does it have? Valence electrons. It's stable. Now this is stable, and let's think it out. It had a 0 charge to begin with. Stable, weird. Stable. It had a charge of 0, and it now has one more negative charge to it. What's its negative charge now? Dang it. What's its charge now?
Negative.
Negative. All right. Check it out. 1 negative. And really, we commonly will do this, and it's really annoying when you see it. If it's 1 positive or 1 negative, I don't usually include the number. Okay. Now, check this out. This is now a stable cation. It's become positive, and this is a stable anion. Now, think about everything we did with electricity, with magnets and all that. I have something that has a positive charge and something that has a negative charge. They want to be balanced in the end. I know that we had to move some electrons to lose balance in one sense. Are those two things going to attract, repel, or not interact? Why would they attract? Wholly opposite charges. Opposites attract, right? Which means when we go through this, and I guarantee we see this more again later, but it's a good place while we're just talking about it. This positive would really like to stick with this negative and balance themselves out. They are attracted at this point. Anybody want to give a shot in the dark to what this is called? It is a compound, you're absolutely right. This very specifically is lithium fluoride, which is just a weird way that we name stuff. Lithium fluoride.
The fluoride stuff that people use, or what type of fluoride?
I do not know the answer off the top of my head. That's a good Google question to remind me later, because I will not remember. Yes, sir. Yeah. All right. So we might have hit that a little early. We will see this again. Does it feel better right now than it did yesterday?
Yeah.
Okay, Lily, are you okay with where that answer went? Like, it just goes to something else. Okay. All right. So metals really like to join with nonmetals because of these charges and the way they interact. Cool. Okay. Last questions before we go on a little bit more about metal stuff. Okay. So it turned. Well, I was waiting. I'm trying to give everybody time to talk up. It's called wait time and teacherese. Like if I say, "Hey, what's the square root of 94?" See, if I don't wait, then I just wind up answering the question.
Yeah.
Do you have it?
No.
Oh.
That's my kid.
I have one more question.
I have one more answer. Maybe.
How do you, like, you know how fluorine only has 7
Valence electrons.
valence electrons? How do you know if it has less, like, less than 4%?
So to decide on when will it become stable, that's a super easy question to address. Good question, but check it out. All of these have 7 valence electrons, right?
Yeah.
How many electrons do we need to add to get from 17 to 18?
1.
Boom. This one, how far away from 18 is it?
4.
So how many electrons do you think carbon will take?
4.
Boom. Yep, you got it. Okay, now, everything that we've seen just now, and I'm not going to write it here, but let's commit this to memory for now. This is known as ionic bonding because we are making ions. Whether it's cation or anion, doesn't matter. Ionic bonding. Okay, opposites attract. Now, turns out that if we were to zoom in and look a little bit more at metals, we get some kind of weird things that wind up happening. So we're going to look briefly, and we're going to define in this section what is known as metallic bonding. Okay. Yeah, bonding metals together. Because all of a sudden this seems weird because we see that metals like to join with nonmetals. Well, we obviously have metals that join with metals because everything that we use, or a lot of the stuff that we use, is made of metal. So, it turns out that in contrast with ionic bonding, if we have 2 metals that only have 2 or 3 valence electrons, neither one of them want to take others because we're closer to being stable by getting rid of them we're both trying to get rid of them at the same time and nobody wants to take them. That's where we're faced with. So, as we look at this, if we were to look at a single metal, and we'll talk about some language that comes in here, when we get metals that have been bonded together, what we get is metal cations, which are those positive or negative?
Positive.
Positive. Metal cations. Turns out they do something crazy. They all share their valence electrons. Okay. Now I'm going to leave a little bit of space here because I'm going to draw a small picture. It's up to you if you want to draw it. Sharing electrons, specifically the valence electrons, is called covalent. They are sharing those valence electrons, but it happens in a crazy way that explains a ton of the properties of metals. I'm going to leave just a little tiny space here in A, and then something blank right here. Here in a minute. I'm going to fill in that line. Okay. As we look at this, you do not have to draw it. I'm going to draw a single piece of metal wire, and we're going to zoom in at a not real to scale idea, but we're going to see it. Check it out. Here's a wire. And I'm going to draw it with tips so that I'm not actually going to be able to. So let me make this a metal. And since it's a metal, do you guys agree that there's probably a bunch of protons floating around somewhere in it? Because every metal will have protons. Okay, so again, not to scale, I'm going to add some red dots for my protons. So check it out. All these little red dots, they're protons. Cool. And they should all be roughly the same size. Anything crazy so far? Now, normally, if we think about all these protons or all these atoms specifically bonding, what would happen if we only had 2 or 3 of them is that maybe they can get stable. Don't draw this dot yet. Maybe they could get stable by sharing that electron like between these two. So they both get to count it right there. And then maybe these two share this one, and so forth and so on. And we can see that they all can share their electrons, and it's a weird idea, but they can all be stable together. Okay, no physical movement of electrons, they just happen to share it, which is a weird idea, but if we think about like, hey, a sandwich can be shared between Ronaldo and I, right? He could take the whole sandwich, I could take it, or we could share it. Maybe we could share it. And it doesn't work with the sandwich analogy, but if Klein was hungry, could we share it with him? I think so, right? Probably. Could I share it with Liam also? Now with the sandwich, I'm going to run out because I'm not going to be able to give you all, I mean, I could probably give all of you a tiny bitey sandwich, but there's a number where I'm not going to be able to, right? Electrons are not physical objects like this. They're weird. What happens in this picture, I'm going to see if this works to shade it or not. In this picture, rather than the electrons being connected to any particular piece, we get this lovely picture. Moment of truth. Hate it, and I don't understand why it didn't work. Yep, doesn't make any sense. We're going to steal this layer for just a second. Okay, if I wanted my electrons in here, rather than just being dots, all this blue region is where my electrons are. And it's weird to say, but they're kind of everywhere all the time. Can you see the negative blue charge in there? Like, yeah, it's everywhere, right? They're all sharing all of their valence electrons. And we don't get a good physical picture of it other than saying, look, all the electrons are in that blue area. It's so like unclear when we talk about these things that we refer to these cations, they're sharing their electrons in a, let me turn that one back on. What layer did I just draw that on? What? There it is. Weird. In a sea of electrons. Now, this is the real true language that's used for this. The sea of electrons in a metal. Now, this does a few things. Because these atoms aren't physically bonded to one another, like they're not stuck because electrons haven't moved, it's not like they're magnets stuck together. The fact that these electrons can move make it really easy if I want to change this. Could I bend it and those electrons move along with it? Okay, that is ductile and malleability. I could roll it thinner and those electrons will just evenly distribute to whatever area that I give them. This property of metals in how they bond to themselves or to other metals allows us for all of those other properties that we see. The fact that I can bend it and it doesn't break is because of what the electrons are doing at that really tiny level. Okay. Now, as we get through here, I'm going to split this up different than I normally do. Okay, you guys are going to be collaborating with one another, and you're going to be helping me to fill in some stuff here in a few minutes. You are going to go through your text. You're going to read it independently or with your neighbors at your tables, and you're going to fill in some gaps about some stuff. Cool. So, I will be calling people in just a few minutes. I'll pause it because I don't have to see it. This evening and starting now, you'd probably be able to knock it out before. Tomorrow, we're going to be talking about some specific groups of metals. Okay, so your option, and not really option, your job right now is from one of the following 4 in your textbook. There are small sections. I want you to read it and take small notes so that tomorrow when we're filling this out, instead of me saying, look, here it is, I will be drawing information from random groups. Okay, these groups that you can choose from, you need to read and give me a short summary of it as like notes. Okay, you can choose the alkali metals. This is one option. The alkali metals. And these are all going to be in your text. You could do a ton of research outside of it, but if you search anything chemistry on Google that's not like really specific, you're never going to get to the end of it. I would use your text. Okay, you can choose the alkali metals. You can choose the alkaline, which is slightly different.
Is that like the batteries?
So definitely related to batteries. The alkaline earth metals. Okay, I will give you guys note cards to jot down your stuff so that it doesn't have to be in your notes. Another option is the transition elements, or transition metals, if you will. Okay, then we get the inner transitions. I don't know why that's so big there. The inner transitions. Okay, for this, we have 5 minutes left in class. Whichever one you and your neighbor want to go through, I'm fine with that. I am going to give the inner transition metals. Alright, so for this, I will come around and give you a piece of scratch paper if you need one. I want you on a piece of scratch paper. Do not lose it. Tomorrow when we go through these 4 different things, I'm going to be asking you guys for a source. I will collect this tomorrow. I need to see that you have read. This starts on page 425. You only have to do one of them. 425 through 428. Between you and your neighbor, pick which group you're going to read about. We have 5 minutes right now. You should just do it right now. It'll take less than 5 minutes. It's like 3 paragraphs. Okay, for this, I want you guys, with your name and the few notes that you're going to take with this, you're essentially just taking notes, but I want to see that you're actually doing it. So, I don't care which group you decide. These 2 might decide to do the transition metals. Maybe these guys do as well, or they do the alkaline. I don't care. You're going to read the few short paragraphs in your text of whatever your group decides on. And I'm going to collect these tomorrow, and I'll throw on your information tomorrow through the lecture stuff.
We're just gathering information.
You are reading through and trying to summarize so that when I'm looking for information tomorrow and say, hey, what can you guys tell me about this? Somebody will be able to tell me about it. Cool. So you have...
Alkaline, transition, or inner transition?
No, but you need to read 3 paragraphs. You're jotting down, summarizing, taking notes. So that tomorrow during the lecture, you guys are going to be shouting out the answers. I'll be right back.
Is it supposed to be the transition notes?
I will do that. If you choose to do the transition elements, I'm fine with it. I refer to them regularly as transition metals. They're the transition elements in your text. Cool. All right. You guys have the next 3 minutes. I think you might be able to finish. It's like 2 paragraphs and a few things jotted down.
If it does, I'll just do the alkaline.
I did not necessarily. But I'm not going to say no because Sonny asks, can I do bullet points? Yes, I love it. Bullet points are easy to read, easy to make sense of. Alkaline. I don't need to pronounce the others. Easiest to do what?
Are
What?
easier or
I don't know. They're all. None of them are bad.
Now, no.